Hello, and welcome to Lesson 31 of this Introduction to Differential Equations with Wolfram U. This lesson will introduce the concept of a system of non-homogeneous differential equations and the methods to solve such systems. As we will see, if any of the differential equations in the system are non-homogeneous, we will need to use a different technique to solve the system, which will involve diagonalizing the coefficient matrix. Let's take a look at an overview of this lesson. In this lesson, we will cover the topic of systems of non-homogeneous differential equations. Such a system of differential equations will take the form here, in matrix form, where capital X is a vector of dependent variables, each with the independent variable t, while G is a vector of functions of only t. As is shown in the plot here, the trajectories of the general solution to non-homogeneous systems of equations can be visualized by specifying the arbitrary coefficients that appear in the general solution. If at least one of the differential equations in the system is non-homogeneous, then we can't use the methods from the last lesson, since they were for solving homogeneous systems of differential equations, so we are required to use different methods. A non-homogeneous system of differential equations can be written compactly in matrix form here, where the non-homogeneous term is represented by the vector G. An example of a non-homogeneous system of equations is given here. In this case, the dependent variables are the functions x1 and x2. T is used as the independent variable, while the e to the minus 3t and t squared terms represent the non-homogeneous parts of the system of differential equations. We can write down the system of equations by first defining the various vectors and matrices that appear in the matrix equation. With the A matrix as well as the capital X and G vectors defined, we can write down the system of non-homogeneous differential equations. The key to solving a non-homogeneous system of differential equations is to diagonalize the matrix A. To understand what is meant by diagonalizing the matrix A, consider the matrix here. To diagonalize A means that we can write it in the form here, where S is a matrix composed of the eigenvectors of A, while D is a diagonal matrix with the eigenvalues of A along the main diagonal. For the matrix A above, let's verify that it can be composed of the S and D matrices in the combination given. First, define the matrix S of eigenvectors. Since the eigenvectors function returns the eigenvectors as a list of lists, they are already returned in matrix form. Next, we can calculate the eigenvalues of A and put them along the main diagonal of a matrix. The diagonal matrix function creates a matrix with the list of eigenvalues returned by the eigenvalues function along the main diagonal. Finally, verify that the matrix A can be written as the inverse of S times the diagonal matrix D times S. We can see that the matrix A can be decomposed in this way, so the matrix A is said to be diagonalizable. A matrix can more easily be tested to be diagonalizable using the Wolfram language Diagonalizable Q function. The method to find solutions involves a technique known as diagonalization. To demonstrate this method, define first the vectors and matrices necessary to construct a non-homogeneous system of differential equations. We can express the system of equations in the Wolfram language to see each term explicitly. What we are going to do is define a matrix T, which is constructed such that the eigenvectors are the columns of the matrix. Then we can define a vector of a new dependent variable y. Defining the vector capital X to be the T matrix times the y vector, the system of differential equations becomes this. To get rid of the T matrix on the left-hand side, Multiply both sides of the equation by the inverse of t. What results is a decoupled set of equations where the function y1 appears only in the first equation and the function y2 appears only in the second equation. As we saw in the previous slide, the transformation of the system of equations led to these two decoupled differential equations. Since the equations are decoupled, we can solve each of them separately using the techniques we've already discussed throughout this course. We can also give these equations to desolve and have that function calculate the solution. We found the y-vector which solves the two decoupled differential equations on the previous slide. In order to get the solution to the original system of differential equations, we need to calculate the x-vector, which can be obtained by multiplying y by the t matrix. This result is the general solution to the non-homogeneous system of differential equations. Using parametric plot, we can visualize the solution when the coefficients are both equal to 1. Let's use this method of transforming the x-vector to solve the non-homogeneous system of differential equations here. Once we have the solution, we will also draw several of the solution trajectories. To begin with, define the matrix A and the vector g from the differential equation, and construct the matrix T from the eigenvectors of A. Next, define the y-vector, which holds the transformed dependent variable. Substituting in the definition for the x-vector in terms of the matrix T times the y-vector, then multiplying the system by the inverse of T gives the system of equations here. Once again, the system of equations has been reduced to a decoupled set of equations for each function y1 and y2. We found the transformed system of decoupled equations on the previous slide and defined them here as equation 1 and equation 2. When we last encountered a set of decoupled equations, we gave desolve both of the equations at once and let the function solve them both simultaneously. However, the primary advantage of this technique is that we don't need to solve the two equations simultaneously. Since they are decoupled, we can calculate the solution of the first equation, like we do here, without ever including the second equation at all. We can then go ahead and solve the second equation without using the first equation at all. However, it is important to remember that since we solve the equation separately, desolve value will use the same arbitrary constant. Therefore, one of the constants must be redefined to C2 so that the two constants are distinguishable. We have now solved the decoupled system for the y-vector. The solution to the system of non-homogeneous differential equations is given by the x-vector, which is related to the y-vector through the t-matrix. Multiplying the y-vector by the t-matrix gives the x-vector, and thus the solution to the system of differential equations. Using parametric plot, we can visualize the path of the solutions for various combinations of the coefficients. Let's now consider a system of three non-homogeneous differential equations. We will find the general solution and plot the solution for several trajectories. Like we did before, begin by defining the matrix A, the vector g, and the matrix of eigenvectors T. We can transform the equation by replacing the variable x with t times the y-vector. Substituting this into the system and multiplying by the inverse of t gives an uncoupled system of three differential equations. We have now decoupled the system so we can solve each equation individually using the techniques we have learned in this course. First, write the decoupled set of equations in a more natural form. We can now give this set of equations to desolve to find a solution for each of the y functions. Extracting the y1, y2, and y3 functions from the result gives us an expression for the general solution in terms of the y functions. Since we solve the equations simultaneously, desolve will use different expressions for each of the coefficients. We have transformed the non-homogeneous system of equations into a decoupled form and solved the decoupled set of equations for the new dependent variable y. Using the y vector as the solution to the decoupled system, we can multiply this vector by the T matrix to get the x vector, which is the solution to the original system of differential equations under consideration. Since we have a system of three equations, we will have three components to the solution vector. Therefore, we will need to use parametric plot 3D to visualize the trajectories for various combinations of the constants C1, C2, and C3. In this lesson, we have extended the capabilities of solving systems of differential equations to include non-homogeneous terms. We learned that a critical component to solving such non-homogeneous systems is that the matrix A must be diagonalizable. We can test if the matrix is diagonalizable with the Wolfram language Diagonalizable Matrix Q Function. After transforming the vector of dependent variables, the system of differential equations can be decoupled into a set of independent differential equations that can be solved separately for their respective functions. Once the transformed dependent variables have been found, we can transform back to find the solution to the original system of non-homogeneous differential equations.